Now we move into infinite sums. So it is our job to identify the value of r, the common ratio. As you can notice, the first term is a, second term is ar, third term ar squared that we are adding up. So the easiest way is to identify or plug in n equal 1 into the terms. So I get this for the first term, which is a. So when I plug in n equal 2, that's the second term, that's going to be ar. So I'm not going to multiply my numbers out. I'm going to get 3 to the 4th. I like to plug in n equal 3 to identify ar squared to make sure I didn't make any mistakes. 2 to the 3rd over 3 to the 6th. So a is 2 over 3 squared. R is 2 over 3 squared as well. And you can see that that works to get the third term. So it does converge, and the sum is a over 1 minus r. Moving to the next one, let's plug in n equal 1. So I get 10, and I will get 7 to the 0 power, so that's 1 in the denominator. The second term, I'll get 10 squared, negative 7 to the 1 power for n equal 2. And for n equal 3, just to make sure it works, 10 cubed over negative 7 squared. So a is equal to 10, r is equal to 10 over negative 7. Since the absolute value of r is greater than 1, this diverges, and there's no sum if it diverges. That means it adds up to infinity. You must split up around addition or subtraction in a sum, so you really have two separate sums going on. You need to find the a and the r for both of them individually. So plugging in n equal 1, I get 3 squared. Plugging in n equal 2, I get 1 over 3 cubed, 1 over 3 to the 4th. So a is 1/9, r is 1/3. So this does converge. So this here has a sum of a over 1 minus r. This one I have to do separately. So I get 2 over 3 squared plus 2 squared over 3 cubed plus 2 cubed over 3 to the 4th. So a is 2 over 9. R is also 2 over 9. So this sum here gives me 2 over 9, 1 minus 2 over 9. And you could add those together. We'll just move on to the next one. Lots of exponents here. You could invest time in playing with them, or there's no addition or subtraction. There is just multiplying in there. So let's just go plug in the terms. So when I plug in n equal 1, I get 3 to the 0 power. I'm just going to go really slow. And I plug in n equal 1, I get 5 to the 0 power. So that all gives me 1. So then I'm going to move on to the next term. So plugging in n equal 2. So plugging in n equal 2 for the second term. So this is a. I'm looking for ar. Plugging in n equal 2, I get 3 times 5 to the negative 1. Plus, and I'm plugging in n equal 3, I get 3 squared times 5 to the negative 2. So that's ar squared. So a is 1. That's easy to identify. It looks like r is equal to 5 or 3 over 5. 3 over 5. Double checking. Did I make a mistake here? I sure did. That should be negative 2. And so it is 3 over 5. So since the absolute value of r is less than 1, it does converge. And the sum, I'll put it over here, the sum will be a over 1 minus r. So this here does not fit the criteria of geometric. So 3 over 3 to the 1 over n power. So this is not geometric. A geometric has to be to the nth power. 1 over n is a root. So this is a case where you do test for divergence. Test for divergence says if I take the limit of the nth term And here, if I take the limit, I get 3 over 3 to the 0, which is 1, so I get 3. If the nth term does not equal 0, then I know the whole thing diverges, because the terms are not getting small. This one here, I want to make sure I separate it and make 2 separate sums. So I have 3 to the negative 2n, negative 5 to the n plus 1, and then subtract, and then do 2 separate sums, and I'll let you finish that. This is the same thing. This is not geometric. This I would use the test for divergence on, and this also does not give me 0. This gives me 3, so it diverges.